are going to address one particular applications of trigonometry um, called angles of elevation and angles of depression. So let's go ahead and get started. An angle of elevation is very loosely defined as an angle by which the sight line from a particular observer has been elevated with respect to the horizontal. So in this case, if this guy, orange shirt, is looking directly ahead in this direction, and his sight is elevated by this particular angle theta to be the black line, or I'll now outline it to be green. This angle created by the two green sides is defined as the angle of elevation. Sometimes we often define the angle of elevation from being from the ground rather from sight, but that's dependent on how it's defined in the problem. The other type of angle that we'll work with is called the angle of depression. That the angle of depression is defined as the angle by which the sight line of a particular observer has been depressed or decreased by a particular value with respect to the horizontal. Note that both the angle of elevation and the angle of depression are defined with respect to the horizontal. That with elevation, the sight line is being elevated by some measure theta, and the angle of depression, the sight line is being depressed or decreased by some measure theta with respect to the horizontal. Note that there's sometimes a tendency for students to say that this red angle right here is the angle of depression. It is not. That is the angle with respect to the vertical. That is not the angle of depression. The angle of depression has to be with respect to the horizontal, this angle right here. If you note that in a particular problem, it happens to be the case that the horizontals are parallel to each other, which of course they are, um, at least for the purposes of this problem, the horizontals are parallel. Therefore, the sight line, if it happens to be a problem where there are two observers, functions as a transversal. And since these two lines are parallel with a particular transversal that intersects those lines, that makes the angle of elevation in this particular problem congruent to the angle of depression because they are alternate interior angles. And the AIA postulate stated that if two lines were parallel and intersected by a transversal, then the alternate interior angles must be congruent. So how can I apply this to a particular situation? Consider the situation one here, in which there is a bear sitting on the ground on a particular island. Sounds fun. And there is an airliner flying above. If I wanted to determine perhaps any value associated with this problem, whether it's the angle associated with the bear with respect to the plane, or vice versa, or the distance between the bear and the plane, or how high up the plane is, any of those values can be found using an angle of elevation and any necessary trig functions. Note again that the angle of elevation is defined with respect to the horizontal. It's that increase, that elevated sight line, or that elevated segment that is between the two objects in the particular situation. Another approach that I could utilize is, if I wanted to reframe the problem, noting that the angle of elevation and the angle of depression for one particular pair of objects are congruent to each other, then I could reframe this problem by thinking of it in terms of the angle of depression with respect to the plane, that this angle would need to be congruent to whatever this angle of elevation would be here as well. In another situation, I want to remind you that it's wrong to state that this angle here made with the vertical is the angle of elevation, or I'm sorry, the angle of depression. That is not the angle of depression. That just is some angle that's measured with respect to the vertical. The angle of depression in this case would be identify what the horizontal is from that observer and find the angle that's depressed with respect to that horizontal. So the blue angle that I've drawn in here would be the angle of depression, as is shown in the second piece of the situation. How might I apply this to a particular problem? Well, this is one of those areas in which I can take the trigonometry that I've learned in the previous parts of the unit and apply this notion of angles of elevation and depression to solve a particular situation or solve for a value. In this first example, the angle of elevation from a sailboat to the top of a 121-foot lighthouse is on the shore, on the shore measures 16 degrees. How far is the sailboat from the lighthouse? Note that in this case, the diagram is drawn for you. That won't always be the case, but it helps to visualize what it might mean in a first few examples. That the sailboat, the angle of elevation is 16 degrees to the top of the lighthouse, and the lighthouse is perpendicular to the ground. Therefore, we can set up a trig function that uses this angle 16 degrees and some given values or some missing values in the diagram. We're told that with respect to the 16-degree angle, the opposite side is 121 feet, and we're trying to find the distance between the sailboat and the lighthouse, which happens to be the adjacent side. We do have a trig function that allows us to do that. The tangent is opposite over adjacent, and I'll just write out the other ones for you as well, just to remind you that the sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. In this case, again, I'll remind you that from the 16-degree angle, we've been given the opposite side length, and we're solving for the adjacent side length. So I should set up a ratio using those values, that the tangent of the 16-degree angle is equal to the opposite over the hypotenuse. I'm sorry, not the hypotenuse, the adjacent. From there, I should be able to solve for this value d, that distance between the lighthouse and the sailboat, by solving this equation typically as I would any other one. Isolate the variable, isolate the d in this case. I can multiply both sides by d to get d times the tangent of 16 degrees, and the d cancels on the right side, leaving you with just 121. And since I'm trying to isolate the d, I divide by tangent of 16 on both sides of the equation. That d is equal to 121 divided by the tangent of 16 degrees. When I pull out my handy dandy calculator and stick that into the calculator, I end up getting a value of 121 divided by tangent of 16 is 421.977, and this is in feet, so 421.977 feet. And I'll note that the convention that we've utilized is that in a trig problem, the side lengths should be rounded to 3 decimal places, the thousandths as it's often called, and that angle measures should be rounded to 1 decimal place, or the tenths place. A second type of problem is a little more complex in using the angles of elevation notion, and in fact, it uses it twice in order to try and find the length or the height of the flagpole in this case. A flagpole is at the top of a building, 300 feet from the base of the building. The angle of elevation from the top of the pole is 32 degrees. That's this whole angle here. And the angle of elevation, just because it's going to the top of the flagpole, and the angle of elevation to the bottom of the pole is 30 degrees. That's this one here, is 30 degrees. Determine the length of the flagpole. If we're able to set this up appropriately in the diagram, thank goodness the diagram is given in this case, we can set up two ratios, noting that I could call the height of the building h. That's just the building height. I don't know what its value is particularly. I'll just call it h for now. And using that as h, the green triangle that's outlined is a right triangle with an angle of 30 degrees. We're solving for the opposite side, the h, and we're given the adjacent side, meaning that we can set up a tangent ratio since it's opposite over adjacent, that the tangent of 30 degrees is equal to the opposite side, h, over the adjacent, 300. On the flip side, I can set up another equation using the larger blue triangle, noting that that entire angle here, that blue outline one, is 32 degrees, this entire angle. It's hard to draw that in. If that's the case, I can call the entire height, the height of the flagpole and the building, I'll just call it a capital H. It doesn't matter what variable you call it, as long as you call it a variable for the intents and purposes of solving. And set up the same ratio that from this 32-degree angle, the opposite side would be the capital H, that the tangent of 32 degrees is capital H, the height of both of them, divided by the adjacent, the 300. If I wanted to solve for just the flagpole's height, well, that would be the entire height of the flagpole plus the building, capital H, minus the height of the building, little h. So what I'm really looking for is the height of flagpole would be the entire height minus the building height, meaning I need to find each of little h and big H. Well, I have two equations that I can solve separately to find those. Let's change it to green. If I wanted to solve for h in this case, I can multiply both sides by 300. H is equal to 300 times the tangent of 30 degrees. 30 is one of those particular values that we know the exact value of, the tangent, but we'll go ahead and proceed forward using decimals in this problem. That 300 times the tangent of 30 is 173.205 feet. Notice, let's just check in the middle of the problem. The height of the building, what it's saying, is 173.205 feet. The second part of the problem is to solve for capital H, which again, we just multiply both sides by 300. 300 times the tangent of 32 degrees is 187.461 feet. What that is saying is the height of the building and the flagpole, this entire thing, is 187.461 feet. So if I wanted to find the height of just the flagpole, I take the height of both of the flagpole and the building, 61, and subtract the height of just the building. And when I do that, I get that the height of the flagpole is 14.256 feet. The problem does indicate to round to the nearest foot, so this would be that this is 14 feet. The height of the flagpole would just be 14 feet. If there are any questions regarding the angles of elevation problems that we might work, or angles of depression, which work functionally the same as long as you identify the correct angle of depression, then feel free to send out